So now we talked about regression. How about classification? What is the difference between regression and classification technically? When you talk about regression, we're looking for the best fitted plane or line, right? How about when we talk about classification, what we try to do? If you tell me there's here inside this class, team A and team B, and you would like to ensure that team A and team B are well separated, what would you do? Yeah, classification, but I mean, what would you do? Forget about the course. Just think in normal life. If you have team A, team B, and you would like to ensure that team A, team B don't cross each other, and you need to make them well separated, what would you do? Let's say boys and girls, we put them separate if you like. Then what do we do to ensure that we are well able to separate between them? What would you do? Let's say if somebody comes from outside, another teacher or another person, and you'd like to tell him how to distinguish between the two groups, what would you do? Sorry? Label them. They are already labeled, but he doesn't need, again, to check one by one and see the label. So we're looking for the solution, what the solution will be. Or let's say you have marbles in one box, okay? And you'd like to separate them. Maybe you have blue marbles and red marbles. What would you do? Classification, but what would you do? Technically, I mean, in real life, won't you put some barrier maybe in between? You spread them inside the box, then you put barrier. This is the right hand side of the barrier would be maybe the blue marbles on the left, right? So this is classification. Classification is finding a way to best split between two groups or distinguish between two groups by putting a barrier or a line. But this line is not best fit. This is just to distinguish between two things. So unlike regression, we're trying to find the best fitted or representative line. So this line, we call it best fitted, or in other word, representative. While in classification, we're not looking for representative line for these data points. We're looking for barrier that best distinguish, okay? That best distinguish between, let's say, blue marbles or green and yellow or whatever. Clear the point? So this will actually help us to distinguish between them. So that means any marble or any point lay on the right-hand side will be for one class. Anything lays on the left-hand side will be for the other class. Now, of course, you may not have 100% classification, okay? Like this case, you see there are some marbles or some circles that do not belong to this class. Maybe these are noise or outliers or whatever, but the point is you cannot have accuracy 100%. It's quite difficult. So you look for the best one, okay? Where maybe can yield accuracy 90% or 95%, which is quite good. So 5% error may be still acceptable, okay? Clear? So try to understand rather than memorize. So don't overfit this course. Try to optimize, best fit this course, okay? So in classification, we find boundaries or barriers that separate data into different classes while minimizing the error. The error here means misclassification. So the error, this one, means misclassification. That means you misclassify some data points, still fine. So you have some portion for error, you still acceptable error. While regression can be best fitted line or curve that minimize the difference between the error here. This is the error for regression. This is the error. The difference between the actual value and the predicted value, like the house price. The best value, maybe the actual value for, let's say, a certain house is 500K, while the predicted value is 490K. So the error here is 10K. We try to minimize as much as possible. Okay. Now, if we're looking for linear classification, one example is logistic regression. So let's assume that you have data. You have data like here. You see some data lays at label y equals 1. So this is label 1. Those at label 1 and these at label 0. At label 0. Here, just to show you that we cannot apply regression. Regression is not about separate between the data, but is about actually best representative of the data. So if any way you apply linear regression will look like this. And eventually you won't be able to split between the data. How you can split between these data and this one? You're not splitting here, you're trying to represent the data. Okay? Or this one and this one. So how you can split between them? The idea is we need to find a way to split these two. Like this line, for example, but regression doesn't work in this way. So regression won't introduce you, doesn't introduce this line. This doesn't introduce this boundary, right? Doesn't introduce this boundary. So it has to find a line that best represents between the data. While as we said in classification, we try to find a line or barrier or boundary that's split or best distinguish between them. So logistic regression is in this case, we apply, as we said, for classification. So don't be confused by saying, oh, this is regression case. No, this is classification. Even if we say logistic regression is used for classification. So logistic regression will introduce like this line, this S line. And now this S line we can use to split between the data as a barrier, as you notice. Okay. However, this logistic regression will introduce value between 0 and 1. So any value can be between 0 and 1. Sorry, this is 0, should be here, 1 here. And this value, we call it probability. So he's going to introduce probability. Okay, so it's going to introduce value between 0 and 1, while regression actually can introduce any value. So if you apply regression anyway here, can introduce any value, can be less than 1, can be more than 1, because regression for continuous value. While classification here in specific logistic will introduce value between 0 and 1 only. Now, how we can distinguish based on this value between 0 and 1 whether the data point or the marble belongs to class 0 or label 0, class 0 or class 1? Then we look to the probability. Let's say we take threshold line 0.5. If the probability is greater than 0.5, then we assume it belongs to class 1. If it's less than 0.5, then it belongs to class 0. Okay, Goshen? Clear? Okay, so clear how logistic regression works? So again, if you like to differentiate, you can say logistic regression introduce only values between 0 and 1, while regression actually will introduce big range of values. It doesn't matter, like the case here. If you take the left-hand side and have regression, then regression can introduce any value. While logistic only values between 0 and 1, and this 0 and 1, we call it probability or logit, okay, or probability. Then we have threshold value, let's say 0.5, that can help us to distinguish between points belong to class 1 or class 2, class 0 or class 1. Okay, so here what we do again, we estimate the probability of an instance belong to specific class, predicting probability that email is a spam, for example, in this figure. Then set threshold, let's say 50%, that means 0.5. In the typical cases, if estimated probability exceeded the threshold, then the model classifies it as positive, let's say label 1. Okay. So instance is labeled 1 if belong to positive class, instances labeled 0 if belong to negative class. So what is the decision? rule. What is the rule that we can find? If estimated probability is greater than the threshold we set, then we predict that this is positive. That means spam. If the estimated probability is less than some threshold, like 0.5, then we predict that this is negative class. That means it is ham. Okay, so ham email should go to the inbox. Spam email should go to the spam inbox. Okay, so the rule as binary, logistic regression serve as a binary classifier. So logistic regression for binary classification. By nature, logistic regression can only work for binary classification. I think we didn't talk about different types of classification, right? Not yet. Anyway, later we talk about different types of classification, but you can keep in mind that logistic is only for binary classification. We have binary, we have multi-class, multi-label, and multi-output. So this one only can work for binary classification. However, in scikit-learn, the one that the library we are using, they have already adapted logistic regression to work on many classes. Yeah, so you don't need to worry about it. Okay, so again, this is summary for what we have found so far. So linear regression, you try to find a linear relationship or linear line that best fit your data. Logistic, you try to find when the dependent variable is categorical. So again, we're talking about classification. Then this one will try to split the data, will serve as a boundary to split the data into two classes. While polynomial is where you have nonlinear regression when the power of independent variable is more than 1. So you don't have only x of 1, x to the power of 1, x to the power of 2, 3, and 4, and so on. So we apply polynomial regression. Okay. Now, other algorithms we're going to also look at is called support vector machine. Support vector machine, what is support vector machine? By the way, support vector machine can work for classification, can work for regression. Later we discuss. But let us just here introduce support vector machine. Support vector machine aim to create a widest possible street that differentiates between the classes. So if you look into this example, instead of looking only for a boundary, linear boundary, we look for a street, right? So meaning this is our boundary. And then we try to look for any boundary because actually we may find many. For example, maybe Chin will tell me we have also this boundary, right? Which is perfectly fine. Can split between the two. How about this boundary? So the idea of support vector machine, not any boundary is going to be selected, only the boundary that yield the widest possible street. That means the margin is widest possible. So if here I draw the margin is very low. You see, the margin is very small. How to determine the margin? The margin, like you draw the line, how to remove? Or maybe this example will determine. So here we have two boundaries, and we draw the margin. How to determine the margin? The margin is like you take the boundary and then start moving to the other side until you touch the first data point from first class. This is the right boundary. Then on the left, same. Okay, so actually, in other words, you calculate the width, the widest margin, and then you have the split in between. So this will be look like street, right? While the other boundary, so here we have two examples, B1 and B2. B2 is another boundary, but B2 will yield smaller street. So which one support vector machine will pick? Will pick B1, because B1 will yield the widest possible street. Okay, so even though we have two solutions here, which are fine to distinguish between the two classes, but support vector machine will work on finding the widest possible street. Why? To avoid overfitting. Because as you have wider street, that minimizes the chance of having overfitting. Okay, to minimize the chance of overfitting. So the goal here to maximize the margin between the decision boundary and the training sample while minimizing the error. The error here means misclassification, right? So the error here means misclassification. So we try to minimize the misclassification. Same, like the main objective of classification is to find a decision boundary. Now, nonlinear, also support vector machine can work on nonlinear cases. So nonlinear cases, we are still looking for decision boundary that help us to distinguish between two classes. If you look to the right-hand side figure, we found that the best way to best split it is by finding nonlinear decision boundary. Our decision boundary should be nonlinear, not straight. Okay, here. In order to distinguish between the red and green classes. So we have red and green classes. So red represents spam emails, green represent non-spam email. So if you use support vector machine can also work on non-linear problem. Later we discuss how. Now, as I told you, support vector machine can work for regression and can work for classification. So remember classification, we look for decision boundary, right? With widest possible street that help us, the widest possible margin that help us to distinguish between classes. How about regression? What we do in regression? In regression, we do the opposite. We find the widest possible street that can fit as many data points in the street as possible. The opposite. So if you forget about this side, the right-hand side, just take where epsilon is 1.5. So here what happened? We find the decision boundary, or actually not decision boundary, we don't call it decision boundary. So here we find the best fitted street that can include as many data points in the street as possible, while minimizing the error. The error here is the data point that rely outside the street. Okay, so support vector machine again can work for two. This is why they call it versatile. Versatile means can work for classification. So that means can work for classification and regression. This is what we mean by versatile. So classification, in case what you try to do, you try to find the largest possible street while limiting margin violation. While in regression, to try to fit as many instances mean data points as possible on the street while limiting the margin violation. Violation here, the data points or instances outside or resided outside the street. While here, the margin violation, here margin violation, we have data points or instances reside in the street. Okay, anyway, these figures, both of them for regression, huh? So don't be confused. These both are for regression. These both figures for regression just show you how epsilon, there's one hyperparameter later we talk about called epsilon, which help you to control the width of the street. Okay, Zian, any question? Chiho, right? Chiho, right? I'm pronouncing your name. Any question? Okay, good. Yeah, keep smiling. I like to see people's smiles inside the class. I'll feel happy. Yeah, we're not coming here like military base. Each one shouldn't smile, just you sit. Okay. Another types of algorithm are artificial neural network, where we discussed a bit about it. So artificial neural network is follow the biology, the brain, how our brain functions. So they found that our brain has neurons, and neurons are connected to each other using dendrites and terminals. So they come up with a similar idea that they build a unit, calculation unit, which actually take the input, whatever input we have, maybe pictures or text, I mean, as embedded value, and then do some calculation, and finally apply what's called a function, step function, in order to get the output. So again, they try to mimic the behavior of the brain. So we have the body, of the cell body, then here we have unit of process to do some calculation, and then we have dendrites on the biology neuron. Here we have inputs, we have terminals for moving the signals out of the cell. Here we have the output signal or the output value. Okay, later we talk when we go also to artificial neural network. And this is called perceptron, single neuron perceptron. In other words, this is single neuron perceptron. Because perceptron can be also single layer. Anyway, later we talk perceptron. So again, we're looking for biology, neurons. And this is where we have ChatGPT and all these AI due to the neural network. If we don't have neural network, you won't see ChatGPT today. So this is how it works. So simply, we have the calculation unit in the middle. So it's going to take the inputs, and we have what's called weights. Later we discuss about for each input. You can think of the weight like it actually marks the importance of the input. And then we keep trying to find the best values for weights and bias. The weights here, you can think of them like theta, theta 0, theta 1, theta 2. Remember when we talk about regression? So same, theta 0, theta 1, theta 2, for example. So the idea is to find, to adjust these weights. These we call them parameters. The weights, we call them parameters. To adjust these weights as best as possible to yield the lowest error. So again, we calculate the error. If this is regression, we calculate the error. Let's say the house value between the predicted house value and the actual house value, and we keep adjusting these weights until we find the best values. Okay, anyway, later also we discuss about artificial, just to give you an introduction.